In this tutorial screencast, we will look at conformational analysis, where we will specifically examine how to draw a chair cyclohexane. So this far we know that organic molecules are not flat, they have three-dimensional shape. So cyclohexane is an important molecule which we need to learn how to draw in chair form. So it's typically represented as such when it's flat. Each vertex represents a carbon that's bonded to two other carbons. We know that carbon has a valency of 4, so it can accommodate 4 bonds. So the other 2 bonds that we're not showing but will show now are hydrogen atoms. So each vertex is a carbon, each carbon has 2 hydrogens, so the molecular formula is C6H12. As such, being a cyclic alkane, it has 1 degree of unsaturation. The reason it's important to know how to draw a chair cyclohexane is that these 2 hydrogens, even though they're bonded to the same carbon, which I'll designate with an asterisk, they're not equivalent. When you look at them in the flat representation, they look equivalent. However, if we examine a model of cyclohexane, so if we star in that carbon, where each of these bonds is to a hydrogen, we can see that they're in different spatial orientations. So we classify bonds in cyclohexane as either axial. So axial bonds are up and down, if you want to think of them that way. So this is an axial bond. Each cyclohexane has 6 axial bonds, so we can think of them as there's 3 on the top face of the molecule and 3 on the bottom face of the molecule. So that's 6 total axial bonds. The remaining 6 bonds to hydrogen are classified as equatorial. So they occur around the equator of the molecule. So how do we go about drawing this? Because it's important when we start learning the chemistry of cyclohexanes that axial and equatorial hydrogens react differently. So we're going to start by drawing a line that's probably at a slight angle here. So we'll draw our first bond in. So that's, say, this carbon-carbon bond here. Now we're going to draw a parallel carbon-carbon bond. So this remaining bond here. Now let's finish off the left-hand side of the molecule. We're going to draw probably a V shape, this bond. And then we're going to draw a parallel bond to that, which is going to be this bond here. So that's going to finish off the right-hand side of the molecule. So here's the left-hand side, and here's the right-hand side. Now what remains to be done is connecting the two through parallel bonds. So here's one, and the remaining bond that's parallel to that is here. So we've just connected these 2 V shapes. So we have the basic chair down. So now we need to put in the axial and equatorial bonds. So this can get kind of confusing when you're figuring out which angle to draw these. So let's go ahead and we're going to dissect the molecule and show that left hand and right hand side. So just with a dotted line. So here's the left hand side, and here's the right hand side. So let's start at the right hand side. Notice this carbon is I'm going to say up. So that's the carbon here. Because it's up, we're going to put in an axial bond. So there's an axial hydrogen, which I'll abbreviate HAX. Now the equatorial hydrogen, the way we're going to draw this bond is out this way, towards the right. So it's going to come down at this angle, HEQ. So let's finish off the right-hand side. If we look at our model, we see that the axial bond on the next carbon is down. So this carbon is down, so the axial hydrogen has to be down. The other hydrogen here, or carbon, excuse me, is also down. So this axial hydrogen must be down as well. The equatorial hydrogen has to point towards the right. So we have to draw it a certain way. Notice in the model that the equatorial hydrogen is up. So it's pointing towards the right and it's up. So we do the same for the remaining carbon on the right-hand side. And we're going to draw it up as well, HEQ. What I want to point out is that all the equatorial bonds are going to be parallel to some other bond. So this equatorial bond here is parallel to this bond here. This equatorial bond is parallel to that that bond there. So when you draw the equatorial hydrogens, they should form a Z or an N shape to show the parallel bonds. So now if we consider the left-hand side, if we go to this carbon here, notice that it's up. Because it's up, its axial hydrogen is going to be parallel to the other carbon that's up. So axial. This carbon here is also up, so its axial hydrogen is up. And finally, we have a carbon that's down, so its axial hydrogen has to be down. And then for the equatorial, now the equatorial hydrogens on the left have to point towards the left. So how do we figure that out? Well, here's a bond. We want to make this bond parallel to it. So that forms our Z shape. So what about this equatorial hydrogen? Well, it's going to be parallel to this bond here. So it has to point to the left, and it's going to be parallel to that bond. And then finally, the remaining equatorial hydrogen, it has to point left, and it's going to be parallel to this bond. So we've successfully represented the flat cyclohexane as a chair. This is what it looks like from a computer model. So keep in mind that there's a right-hand side, a left-hand side, and the hydrogens have to be drawn appropriately. What we don't want to do is start drawing equatorial hydrogens inside the ring. Every bond should be outside of the ring. Another common thing you'll have to examine in problems in organic chemistry is using Newman projections to determine reactivity. So say we wanted to look at a Newman projection of a cyclohexane. So a Newman projection, we're going to look down a carbon-carbon bond. So we're going to put our eye in the plane of the whiteboard and look down this bond here, this carbon-carbon bond. And it's going to be a double barrel Newman projection because we're also going to look down this bond here. So the Newman projection is already represented by this 3D model here. So we're looking down, this is the left carbon-carbon bond, this is the right carbon-carbon bond. So how do we draw that? So let's go ahead and start by drawing in our rear carbon. So this is, we're looking down this bond now, and we're going to draw our rear carbon on this carbon-carbon bond. And notice we're looking down this bond, so let's put in this axial hydrogen first. So on this left carbon here, the equatorial bond is going to go to the left. And now when we're looking down, this bond coming off to the right is going down to a carbon atom, and that's what's represented by this carbon here. So you can see that this is also going back up to the front carbon. And when we're looking down this bond now, we can see that the axial hydrogen is up. And then that's equatorial hydrogen is off to the right. So now we're going to put in the substituents of the rear carbon. So the circle is actually the rear carbon. Now we're going to show the substituents coming off it. So we can see we have hydrogen equatorial, hydrogen axial, and then this carbon-carbon bond. So we're looking down this carbon-carbon bond. The equatorial hydrogen in the back is coming off here. This axial hydrogen is coming down. The carbon-carbon bond here is coming up to this carbon, back down to this carbon. We have equatorial axial, so H equatorial, and then finally H axial. So this is a double barrel Newman projection that is useful in determining basically elimination reactions of cyclohexane molecules. So this has been a tutorial screencast on the conformational analysis for drawing chair cyclohexanes.